Look closely at any biological system, and you will find a relentless drive toward equilibrium. When two different chemical concentrations meet, the natural world automatically attempts to equalize them. You can observe this directly when a dehydrated organic object, like a shriveled raisin, absorbs moisture from its environment to match the surrounding liquid. This process is called osmosis. But this equalization doesn't happen freely. It is mediated by a strict gatekeeper, a semi-permeable membrane. Every cell in a biological organism is wrapped in one. The rule governing this membrane is absolute. It allows solvent molecules, like water, to pass through, but blocks heavier dissolved solutes. Because the system is trying to equalize the concentration on both sides, the water moves strictly from the dilute solution into the concentrated solution. This microscopic passive transfer of water keeps plants alive and human cells functioning. Yet, we use this exact same mechanism to build massive, high-pressure industrial purification systems. To build those large-scale systems and secure fresh water, engineers first had to translate nature's intrinsic drive for equilibrium into a strict mathematical formula. To isolate this mechanic, we can use a standard thermodynamic model. This diagram shows a glass U-tube. On the left is a dilute solution. On the right is a highly concentrated solution, separated at the base by a semi-permeable membrane. At the microscopic level, the membrane acts as a physical filter. The smaller water molecules easily slip through the microscopic pores, while the larger solute particles are physically too massive to cross. Because the solute cannot move to the dilute side, the water molecules rush in to dilute the concentration. The volume of liquid physically shifts, pushing the water level on the right visibly higher. This identical mechanical process occurs in soil, driving water upward into the roots of plants to dilute the concentrated sap inside. This inward flow is continuous. It generates a measurable physical force that will push that column of water infinitely upward until it is ultimately halted by gravity or a counteracting external pressure. By applying physical force against that rising column of water, we can directly oppose the flow of osmosis. The exact minimum external pressure required to push the liquid back to equilibrium and completely stop the flow is known as osmotic pressure, represented by the mathematical symbol pi. We calculate this threshold using the Van't Hoff equation. Pi equals the concentration of the solution multiplied by the ideal gas constant and the system's temperature in Kelvin. Crucial to this equation is the variable I, or the Van't Hoff factor. If we dissolve a salt like sodium chloride, it splits into two ions, doubling the particle count compared to a substance like sugar, which remains a single molecule. Because the resulting pressure is identical whether those particles are tiny ions or massive proteins, we define osmotic pressure as a colligative property, one determined strictly by the number of particles in a solution rather than their chemical identity. This mathematical framework was established by physical chemist Jacobus Henricus Van't Hoff, linking chemical thermodynamics to the mechanics of liquids. Because this equation yields highly accurate results at standard room temperature, measuring osmotic pressure remains the preferred laboratory method for calculating the molar mass of sensitive, large macromolecules like proteins and polymers. By isolating and calculating this exact force, researchers mapped the absolute limit of the biological process. When applied to human biology, this mathematical limit dictates cellular survival. We measure this through tonicity, the relative concentration gradient between a cell and the fluid surrounding it. If a cell is placed in a hypotonic environment, where the surrounding fluid is less concentrated, the external osmotic pressure drops. Water violently forces its way into the cell to dilute it, causing the membrane to swell and ultimately rupture. Conversely, in a hypertonic environment, the surrounding fluid is too concentrated. The cell is rapidly drained of its water, causing it to shrink and collapse. Cellular health requires an isotonic state. This is where the osmotic pressures inside and outside the membrane are perfectly matched, allowing water to transfer safely without structural damage. In human medicine, a 0.9% sodium chloride solution is strictly utilized because it is perfectly isotonic with human blood plasma. This precise concentration ensures intravenous fluids can be administered without bursting red blood cells. Every cell in your body operates on this strict mathematical threshold. Even a fraction of a percent shift in osmotic pressure results in structural failure. Our model is at a standstill when the piston matches natural osmotic pressure. But when external pressure exceeds that limit, the flow completely inverts. This is reverse osmosis. Pressure forces water backward through the membrane, trapping impurities and yielding a steady stream of pure solvent. Reverse osmosis does not exist in nature. It is a brute force technological intervention constructed by exploiting our knowledge of nature's boundaries. This single principle, applying intense mechanical pressure to a membrane, scales up directly to form the architecture of modern municipal water purification arrays. It is the central mechanism behind seawater desalination. Coastal facilities separate pure water from ocean brine by operating massive pump systems well above the osmotic pressure of seawater. The exact same engineering isolates toxins in industrial wastewater treatment, extracting clean water from chemical runoff. The two processes operate in direct opposition. Natural osmosis strictly moves water from a dilute solution to a concentrated one. Reverse osmosis forces water backward. Osmosis is an unpowered drive toward equilibrium, while reverse osmosis demands intense energy and pressure strictly to achieve purification. By defining the strict thermodynamic laws governing biological equilibrium, we calculated precisely how much mechanical force was required to break them. In doing so, we developed the capacity to force nature backward and manufacture our own supply of clean water.